All right, this video is for AP Calculus, and we're going to talk today about the first and second derivatives test. And this is a really big topic. We usually teach it over a couple days. I think in AP Calc AD, this would probably be an entire week devoted to this topic because there's so much to know about how the derivative relates to the shape of a function curve and how you can use it for things like optimization. We put this into a single unit because we're going more quickly here. This lecture series is intended for like a Calculus BC class where people are mainly needing to review this material from learning it in a previous year, but we will cover it completely. So we're going to split this video into two parts. The first part will cover kind of the basic explanation of first and second derivative tests and the function for curve sketching. And then in the second part, we'll talk about optimization and focus on some questions that are like the AP exam would ask. All right, so the first derivative of a function gives what we call the instantaneous rate of change, or you can call it the slope. It's really the slope of the tangent line at up to a function curve. And there's a unique value for the first derivative at each place on the function curve, or at each x value, right? So the sign of the derivative tells me whether or not the function is increasing or decreasing. So if I were to say, just noting a couple things about this particular function here, there's places where the function is going up, like there and there. Going up meaning that the y is increasing as the x increases from left to right. And there's places where this function goes down, right? Anywhere this function is going up, the slope is positive. In other words, if I were to attach a tangent line to any place along here, the slopes of all those tangent lines are positive, right? And that means that the first derivative will be positive, right? The second derivative, or the first derivative of where we have a place where the function is going down, those would all have negative slopes. So there's a negative tangent line, negative slope tangent line, negative slope tangent line, negative slope tangent line, and so on, right? So we would have a negative first derivative, where we would say the first derivative f prime of x is less than 0 in these locations. This is another notation that you might see. F prime of x being greater than 0 in these locations. Right? And the terminology we use is increasing. F is increasing when the derivative of f is positive. And f is decreasing whenever the derivative of f is negative. Right, so you can kind of, below a curve like this, you can make, I like to call it a slope map, right? Some teachers have referred to this as a wiggle graph or something like that, right? But the function is generally going up wherever the first derivative is 0, and it's generally going down wherever the first derivative is negative. Okay, now the places where it changes from going from positive to negative, those are called critical numbers. If we're talking about the x location, and if we have points attached to them, those are called critical points, right? So something is critical when the first derivative changes sign, or it has the potential to change sign. So if you want to locate where that might occur, where a function is about to change from positive to negative, in other words, it's going from increasing over here to decreasing over here, right at that location where it's changing, the slope here is 0. Right? The value of the first derivative at that location would be 0. And that's true also here, where we're changing from decreasing to increasing. The first derivative could be 0 at that location, right? Also, we could have something like this. Now, this particular sort of a thing is called a cusp, or sometimes referred to as a corner. A corner is more when we have a change like this. And if you have two things that come to a point, typically that is called a cusp. This is referred to as a corner. And at those locations, that abrupt change means that the first derivative at that location does not exist. Right? So we could have a sign change there. We could go from increasing to decreasing, either at a place where the first derivative is 0 or wherever the first derivative does not exist. So if you want to identify the critical numbers, the x coordinates where the derivative might be changing sign, or where the sign of the first derivative may change, then you just test for all the places where the first derivative is either 0 or does not exist. And notice that just because we have identified a critical point doesn't mean that the function necessarily has to change direction. Here's a location over here where the first derivative is 0 because the slope of the tangent line is 0, right? And yet this function is decreasing, and then on the other side of it, it continues to decrease. In other words, we're going from negative to negative. So these locations here, the critical locations, are places where the sign of the first derivative may change, but it does not necessarily have to change. It does change there, and there, but it does not change at this one. So this is the only one where we might have a potential change there. All right, so the way we detect a critical number, that occurs whenever the first derivative is 0 or does not exist. So the first derivative test is when we want to establish something about the curve by locating the critical values. Once we locate the critical values, we divide the domain up at those critical values, and then we test a point. So here's the critical point, or critical value, critical point, right? So then we just divide this up, and we pick one value that's inside each of these ranges to test. And by test, it means we're going to plug that x value into the first derivative and just determine if it's positive or negative. We're trying to test to say, is this positive? This one happens to be positive, that happens to be negative, that happens to be positive, that's negative, and that's still negative. Okay? So by testing, we can build a slope map and get an idea for where the function is increasing and where the function is decreasing. Right? From that, depending on the sign at those test values, we can sketch in a little picture to say, okay, the function is increasing here, increasing, decreasing, and continues decreasing. And note that, as we said before, just because there's a critical value doesn't mean that we definitely have to have a sign change. So it's not sufficient to do this. Some people think, oh, you can find all the critical values, test the first one, and if that's increasing, the other ones always alternate, plus, minus, plus, minus. That's not necessarily true. Any of these ones in here might have the same sign. So you have to test in each individual range in between the critical values in order to figure out what's going on in the function curve shape. Now, if you have a critical point where the function is increasing coming up to it, so it's increasing on this side, and then it's decreasing here, that means the critical value itself is sitting on the top of a hill. We call that situation a relative maximum or a local maximum, meaning in that neighborhood, this is the largest y value in that region, right? You're sitting on top of a hill, right? Local minimums also occur at critical values, except that's when the sign for the first derivative changes from negative to positive. So if we're sitting at the bottom of a valley, this is called a local minimum. Right? Here's a critical point that came because we have a cusp. This went from increasing to decreasing. Since that's from up to down, that means this point is also a relative or a local max. However, this location here, even though the first derivative is 0, and it could change sign, the fact that it went from decreasing to still decreasing means it's neither a local maximum nor a local minimum. So we do not have a name for that situation. Okay, so local max or relative max means you're sitting at the top of a hill, relative or local minimum at the bottom of the valley. Okay, so that's the first derivative test, and the first derivative gives me information about the places where the function is increasing and decreasing. Okay, the second derivative test is about the second derivative, so the derivative of the derivative. So to analyze that, let's imagine that we drew some tangent lines on this function curve. Like, let's put a tangent line at this x right here, x is a, and that looks to me to be a slope of around 2, so I'm going to put the number 2 there. Here, the tangent line at this x value is 1, the tangent line at this value is a half. Here's a critical point where the tangent line is 0. Here the tangent is negative a half, negative 1. The slope of this tangent line is negative a half, then 0, then positive. So what I've done here is written my estimate of the slope values of the tangent line, so the value of the first derivative. Okay, so remember the second derivative is the derivative of the first derivative. That means it's supposed to be a number that represents how the first derivative values are changing. So all these blue values here, they're all going down. If you agree, we went from 2 to 1 to 5 to -0 to -0.5, all the way to here. the first derivative is decreasing, right? So that means this derivative is negative, right? And that means that the second derivative would be less than 0 here in this region. So whenever the second derivative of a function is 0, it has this characteristic shape where the function curve is curving down. That situation we call concave down, and we refer to this second derivative. The second derivative is called the concavity of the function f of x, provides something called the concavity. Right? Concave down is whenever that second derivative is 0, and that means that the curve is like a cup that's upside down. Okay? Now, let's look at what these blue slope values are doing. They're going from -1, right, to -1 to -0.5 to 0 to 0.5 to 1 to 1.5. So in this region, right, these values are increasing. And that means that the second derivative is greater than 0 because the first derivative's values are increasing, so its derivative is positive. We call that situation concave up. And for concave up, we have a curve shape that is curving in an upward way. So that would be here. Just on the other side of this critical point, which is at a cusp, we have something which is decreasing, but it's still curving up. It's still curving up because the slopes are going from -3 to -1 to 0, which means the slopes are increasing. Right on the other side of this point, though, the slope now begins to decrease again. Right? So this curve switches from concave up to concave down. To kind of keep it straight, you can think of it this way. Concave up, that's when the second derivative is positive. And positive things make us happy, right? That means that curving up is associated with the second derivative being positive. Concave down, when the second derivative is negative, is when the curve is down, and negative things make us unhappy. So, right, downward curving, second derivative negative. Upward curving, concave up, second derivative positive. Well, we said that when the sign of the first derivative changed, we call that situation a critical point. There is a name for the second derivative changing sign as well, and it's called an inflection point. So an inflection point are the x values, well, inflection values are the values of x where they happen, and if you have a point there, it's called an inflection point. That's the place on the curve where the curve changes from curving down, concave down, to curving up, concave up. So this would be an inflection point. Right? This would also be an inflection point because we're changing from curving up to curving down. This point, while it's a critical point, is not an inflection point because the curvature was concave up on this side and is still concave up on this side. So below a curve here, we could look at the signs of the second derivative and make what we might call a concavity map. Wherever the second derivative is negative, the curve has a generally downward curving shape and an upward curving shape where it's positive. Upward curving in this region, downward curving in this region, changing at potential locations of inflection points. So if I were to put both of those things on the graph, we should know a couple of things. Critical points and inflection points may or may not occur at the same location. Often they don't. Like critical points, when we change from increasing to decreasing, that occurs here, here, and here. Right? Inflection points are about when the curvature changes, and the curvature changes usually in the middle of a region between two critical points. So most inflection points are in the middle of other regions. Okay, so we can, how can we use these derivative tests? There's basically a couple of things. We could be given, if we're given information about a function, like we know f of x is this, we could, we could be given information about a function in different ways. We could be given the function expression. We could be given a graph of a function. We could be given the graph of the derivative of a function, or rarely the second derivative. Or we might be given a word problem where we have to use the words of the problem to build the function. So somehow we'll have some way to get information about a function. And then you can use the first and second derivative test to answer questions like, where are the critical points, and where are the x intervals where f of x is increasing or decreasing? Where are the inflection points, and where are the x intervals where the function is concave and concave down? We could use this to find the location of any relative or local maxima or minima points, and together maximums and minimums together are called extremum or extrema. The plural is extrema. Or you could find absolute maximums and minimums of a function over a given interval, which we'll talk about that later. There's an extra part to that. Or sometimes we want to find the optimum value or optimize the value, find the maximum or minimum value under some constraint. Like if we have only so much fencing to fence in this lot, how could we arrange that fencing so that we maximize the area? That could be locating the critical points where we can figure out where the area function is maximum. That'll be at a local maximum. All right, so we'll look at all these throughout the rest of this. First of all, let's say it says find the following for f of x. We're going to be given a function, and we want to find the critical points where the x and y values are increasing and decreasing, find inflection values, and where it's concave up or down, find the location of any relative maximum or minimum, and any asymptotes. And then we'll sketch the function. All right, so I'm going to show you a kind of a big procedure here that you can use to evaluate these. And these two examples will finish this first half of the lesson. We'll finish the video after these. All right, let's go ahead and let's get 2 copies of these things. And we'll look first at problem 1. Now this is going to seem like a really big point, and we won't ask a lot of questions like this on tests just because they're so time consuming to do, but really understanding everything that's going on in an example like this just gives you a lot of information about how to interpret the use of the derivatives. So although we're going to do a lot of things in this example, you can build lots of little smaller questions from pieces of the procedure. All right, so my goal here ultimately is to sketch this function without using a plug. So let's look. First of all, they're asking me for critical points and x values. I think in this case, I'm actually going to do a couple things. Let's just do the first derivative test. So for the first derivative test, I'm going to take the first derivative. So let's go ahead and find the first derivative here. F prime, that's E-N-O-R. So that's fine. Okay. So for the first derivative test, we'll start by taking the first derivative. This is a quotient, so we'll do quotient rule. So low, derivative of high, which is negative 2x minus 4, minus high, negative x squared minus 4x minus 7. Derivative of low is 1 over low squared. Now normally we wouldn't do a lot of simplifying, but because we need to use these functions, let's do some algebraic manipulation to simplify this. So this f prime of x, first of all, I think I'll just multiply the whole thing out and hope I can get some cancellations and stuff. So doing FOIL here, this is going to be negative 2x squared, and then I've got minus 4x, minus 6x, minus 12, and then distributing this negative here, plus x squared, plus 4x, plus 7. I'm going to leave the x plus 3 squared factor like that. Okay, do we have, let's combine like terms, f prime of x. Negative 2x plus 1x is negative 1x squared. We have negative 4, negative 6, that's negative 10. Actually, this negative 4 and this plus 4 cancels, so that's negative 6x. And then we have a negative 12 plus a 7, so that is negative 5. Right? Make sure I don't introduce any problems here. Okay, and that's still over x plus 3 squared. Okay, that actually can be factored. We can take a negative out of the top and factor the resultant polynomial and get that this is x plus 1 times x plus 2, or sorry, x plus 5 over x plus 3 squared. And I don't think we can make it any more compact than that. All right, so the goal is to figure out what the critical points would be. So let's do that. Critical points, or critical values, they're going to happen whenever the first derivative is 0. Right, so this will be 0, negative x plus 1, x plus 5 over x plus 3 squared will be 0, since this is a fraction whenever the numerator is 0. And that will occur at x is negative 1, that makes this part 0, or at x is negative 5. So there are two places where we could have that where we're not f prime of x is equal to 0. But also, we could have a critical point whenever f prime of x is undefined. And that will happen when the denominator is 0. So that occurs at x is negative 3. So I actually have three values here where the first derivative is either 0 or not undefined. And we could have sign changes at each of those. Now I'm going to take the domain, which in this case would be all the numbers, right, from negative infinity to infinity, except for negative 3. And I'm going to split this apart. Let's see, negative 5 is the lowest of those values, negative 3 and negative 1. And then I'm going to select some test values in each of these. And we will test this in this first derivative. Right, so let's pick negative 6 in this region. For this value, we'll pick negative 4. In this region, we'll pick negative 2. And in this region, we'll pick 0. The goal is to figure out f prime at those locations. So f prime of negative 6. Now, all I really care about is whether or not this is a positive or negative number. So I want to know if the first derivative is telling me the function curve is increasing or decreasing. So I've got a negative here. There's a negative there. X plus 1, if I plug a negative 6 in, will be a negative. So that's going to be a negative. Negative 6, this is a negative 6, right? Negative 6 plus 5 would be a negative. And then whatever this is, it's squared, so that makes it a positive on the bottom. Three negatives together are negative. Negative divided by positive would be negative. So I'm going to assert that f prime of negative 6 is less than 0. What that's telling me, the first derivative of 0, is that the function curve goes down in that region. So I like to put a little mark like that. We're going to do that for each of these test points. Negative 4. So we have a negative out front, that's not changing. If I plug a negative 4 in, that factor is negative, but negative 4 plus 5 is positive. And then this is positive on the bottom. This is positive over positive, so f prime at negative 4 is greater than 0 or increasing. The function curve is increasing. Okay, at negative 2, we would have a negative, nope, negative 2 plus 1 is negative. Negative 2 plus 5 is positive. So that means negative over positive, or positive over positive. F prime at negative 2 is positive, so still increasing. And then if I plug a 0 in for the x's, I have a negative, a positive, and a positive. So f prime at 0 is less than 0, and that's negative. So I can already tell that the function curve goes down and up, then continues up, and then goes down. So it has roughly this shape. And I can already get an idea, rough idea of the shape. Okay, to get more finely tuned, we're going to use the second derivative test. So the second derivative test, we have to take the derivative of the first derivative. So I'm going to go back to this version. Use a different color here. I'll use this color. Now I'm using this version right here to take a derivative of. So the second derivative is going to be, I'll do quotient rule again. That's going to be low, which is x plus 3 squared times the derivative of the high function, which is negative 2x minus 6, minus the high function, negative x squared minus 6x minus 5, times the derivative of the low function, which is extended power rule, 2 times x plus 3 to the first power times the derivative of the inside, which is 1 over x plus 3 squared, which is to the fourth power. Okay, let's try to boil this down a little bit. This second derivative is going to be, well, I'm thinking I'm going to leave this out here, but let's multiply this part out. Actually, I might need to just multiply it all out. This bifoil is going to be x squared plus 6x plus 9 times negative 2x minus 6. And I've got minus, I've got a 2 here. And then let's multiply each of these things by this x. So x times this is going to be negative x cubed minus 6x squared minus 5x, and then everything times this plus 3. And it's going to be minus 3x squared minus 18x minus 15. And then that's all over x plus 3 to the fourth power. Okay, second derivative. Now I need to multiply all of this by that. So let's see, this is going to be multiplying all this by negative 2x. That's going to be negative 2x to the fourth, negative 12x squared. That's a 9. 2 times 9 is 18, negative 18x, and then everything in here times negative 6. So negative 6x squared, negative 36x minus 54. And then everything in here times a negative 2. So negative negative is positive 2x cubed, negative negative positive 12x squared plus 10x plus 6x squared plus 36x plus 30. Wow. Okay, over x plus 3 to the fourth. Okay, let's see if we can gather some like terms up. X to the fourth, that's the only one we have there, so that is, I've got this worked out already, so I'm just going to make sure this all boils down. All right, this video has gotten pretty long. I'm just going to jump to the chase. If you very carefully simplify this, you end up getting this. You can factor it all the way down to 2x plus 3 times, actually it boils all the way down to this. It boils all the way down to negative 8 over x plus 3 cubed. Okay. So now, we're going to do the same thing we did over here, where we're going to find something like the critical points, but now these are called inflection points. I'll change colors here. Okay, to find the inflection values, we're looking for places where the first derivative is 0, or, second derivative, or the second derivative does not exist. So negative 8 over x plus 3 cubed would be 0 only if the numerator was 0, so that does not occur. There are no places where that's true. But this would be undefined whenever the denominator is 0, right? So negative 8 over x plus 3 cubed is undefined at one value. X is negative 3, because that would make me divide by 0. So that means I have to take my number line from negative infinity to positive infinity and divide it at negative 3. And then we're going to take test values inside each of the regions. So maybe we could take like negative 4 and 0 as test values. And then let's plug it into this to evaluate the second derivative. So we have a negative on the top. And then if I plug a negative 4 in here, that's going to be a negative cubed, which is negative on the bottom. So that means that the second derivative at negative 4 is positive, which means concave up. Right? And if we do the same thing with 0 plugged in, we have a negative on the top. We have 0 plus 0 is a positive cubed on the bottom. So that means that f double prime at 0 is less than 0, so that's concave down. Okay, now that gives me a lot of information about the curve shape. Right? So we're going to do a couple more things here. This asks me first to find the critical values in the x intervals where we're increasing and decreasing. So I'm going to summarize all this on the next page here. Let's make a summary. This function is the critical values are negative 5, negative 3, and 1. So let's go to the next page and we will summarize this. I'm just going to write all this. Critical values. X is, let's see, we said negative 5, negative 3, negative 1. X is negative 5, X is negative 3, X is negative 1. Okay, then it said that we want to find the X where we're increasing or decreasing. So this function is increasing from -5 to 3 and increasing from -3 to 1, -1. So let me say this, f is increasing from -5 to 3. I'm going to use interval notation and -3 to 1, -1. And it is decreasing on the other intervals. So from -infinity to -5 and from -1 to infinity, those regions are where it's increasing. Okay. Do we have any local maximums or local minimums? Well, here, where this -5 is sitting at the bottom of a valley, so that is a local minimum. Let's actually figure out what the y-coordinate is at that location. So use a different thing. What would f of -5 be? So I need the original function here. If I plug -5 in here, there's a no calculator for this, -5 squared minus 4 times -5 minus 7 over -5 plus 3. Right, that turns out to be, jump to the chase here, 6. That turns out to be equal to 6. And while we're at it, that is a local minimum. So that means this point down here is -5 for the x, 6 for the y, and that is a local min. It's in the bottom of the valley. And this point is at the top of the hill, so that is a local maximum. And for us to figure out the y-coordinate, we can take this x-coordinate of -1 and plug it into the function. So f of -1, since we're running out of time here, that turns out to be -1. So I'm going to add that. -5, 6, and -1, 1 are. So we've got a local min at -5, +6, and we have a local max at -1, -1. Get those numbers. Okay. Right, then we could do the same thing over here. We do have a change in sign on the second derivative here, so that is at -3. If you plug in f -3 into the function, you'd end up getting, that is, let's see. Oh, that's actually undefined, right? Because if you plug -3 into this function, you divide by 0. So that does not exist. So there's actually no inflection points here. No inflection points. But there is an inflection value at x is -3. So I'm going to note that. There is an inflection value. Actually, let me use the same kind of things and use up there. So if I go here, this is kind of inconvenient to do on that screen. Let's say if I go to this and make this purple. Okay, so from the second derivative test, we found an inflection value at x is -3, but there's no point there. There's no inflection point because there's a vertical asymptote there, right? Because we're dividing by 0. All right. Now, just with that, oh, we should also say where this is concave up and concave down. F is concave up. Let's see, concave up from -infinity to -3. And -infinity to -3. And F is concave down from -3 to +infinity. All right, with that, we should be able to make a rough sketch. So let's go ahead and fill in all that information. First of all, I'll draw an axis here. Looks like more stuff's happening on the left side, so I'm going to draw an axis like this, x, y. Let's see, could I go ahead? Yeah, let's put some type marks on here. 1, 2, 3, 4, 5. 1, 2, 3, 4, -5. Okay, so some things to note. What do we get from the first derivative test? From the first derivative test, we've got this information up here. We've got that there's a critical point at -5, so I'm going to put a dashed line here, also at -3, and also at -1. We also learned that the function was increasing from -5 to -3, continued to increase there, but it was decreasing from -infinity to -5 and decreasing from -1 to infinity. We also know that there is a local minimum at the point -5, 6. So if I go -5 to +6, that's this point right here. That is a local minimum, which means the function curve has to look something like that. And there's a local maximum at -1, -1. So this is a local maximum, so the curve has to look something like that. All right. Also, there is a vertical asymptote at x is -3. So let me change colors here for what we can get from the second derivative. The second derivative, I'll use green for that. So at x is -3, the whole function curve, has a vertical asymptote, but there's also an inflection, a change in curvature there, because this is concave up all the way from -infinity to -3 and concave down from -infinity the rest of the way. Right, so that means that if you look at just the first and second derivative, that tells me the curve shape. So I'm going to use red now. In this section, from -infinity to -5, the curve shape has to be decreasing but concave up, so it has to have a curve shape like that. This has to be curving up while going up, so it has to have a curve shape like that. This one has to be going up and curving down, so it has to have a curve shape like this. Going down, decreasing, and curving down, so it has to have a shape like that. And I know that they have to touch at this location, and they have to approach this asymptote, and they have to go through this point. So matching these curve shapes, I can sketch in the function curve. This looks like this, and this does something like this, and this goes off to match this asymptote here, and goes off to infinity like that. So this red shape, this is the rough shape of the sketch of the curve without ever using a calculator. Now, if you wanted to be more precise, you could find other things too. Like I could plug 0 into this function and find exactly where this crosses this axis to make that more accurate. But this is sufficient for our purposes. All right. That is a serious lot of work. Let me do one more example. I know the video is getting very long, but this is a good part to include in here. If you don't want to see the other example, you can just stop at this point. I'm just going to show you one more example of the same kind of thing. Right? But you could also try this on your own and see whether or not you can get this effect on your own. So what we're going to do next is this curve. So it is not a rational curve. This ought to be, well, maybe it's also a fourth order curve. Okay. I'm going to do the same thing, but actually I'm just going to take this and move it to its own page here and work with that. So if you want, pause the video, try it on your own. To investigate is using the first and second derivatives. First derivative test, I'll take the first derivative, which is, let's see, first derivative is 24x cubed plus 36x squared. Okay. Critical points we can evaluate by finding where is that first derivative of 0, or wherever that first derivative does not exist. This is a polynomial, so it exists everywhere, but there are places where this is 0. This is 36. I can factor out the 12 and an x squared, leaving the 2x here plus a 3. Right? Yes, and then that means that this can never be 0, but x could be 0 there, and also if x was -3/2, this would be 0. You just set that equal to 0 and solve. And there's no additional values. So those are the only two critical values, x is 0 and x is -3 halves. So we'll take a number line and we'll split it apart at -3 halves and 0. And we'll test some values here. Use a different color. So if I test the value, say -2, in this region I'll test -1, and in this region I'll test 1. I'm testing into this, which is the factored version of the first derivative. The 12 is positive. That's positive because it's squared. And then if I plug a -2 in here, that would be -4 plus 3 is a negative. That would be a negative, which means that f prime of -2 is negative, and therefore the function is decreasing. If I plug a -1 in here, positive, positive, 2 times -1 is -2 plus 3 is positive. So that means f prime at -1 is greater than 0, so that tells me it's increasing. If I plug a positive 1 in there, I'm going to also have a positive. Positive times positive times positive, so the first derivative at 1 is greater than 0, that's positive. That means there's only one candidate here for a local min. That's going to be a local min. The x-coordinate is -3 halves. If we plug in -3 halves to the function, you end up getting, I ended up using a calculator and getting 9.875. Right, so now I know there's a local min there. It's decreasing here, the function is increasing there, increasing there. There are two critical values. That all came from the first derivative test. Okay, now let's switch to the second derivative test. I'll use purple for that. Then we take the derivative of the derivative. So the second derivative here would be, let's see, that turns out to be 72. So 3 times 24, 72x squared plus 72x. We're looking for inflection information now. So wherever the second derivative is 0, or wherever the second derivative does not exist, that's a polynomial, so it exists everywhere, but 72x squared plus 72x equals 0. We can factor out a 72x and get x plus 1. So the places where this is true are at x is 0 and x is -1. Those are the two inflection values. If we take a number line and graph, we'll break it apart at -1 and 0. And then we'll test some values here. So let's see, I can test, if that's a -1, we can test -2, -1/2, and we can test 1. So I'm testing into this, which is the factored second derivative. 72 is positive. X, that would be negative. If I plug in a -2, and -2 plus 1 would be a negative. So that's negative times positive is positive. So that's going to be f double prime of -2 is positive, which tells me the curve is concave upward. -1/2 would give me positive, negative, positive. So that would give me a negative second derivative at 1, -1/2. So that's concave down. And if I test 1 in here, I have positive times positive times positive. So f double prime of 1 is greater than 0. That is concave up. All right, so there are two places here where we have a change. One is when x is -1, and if you plug -1 into the function, you end up getting 14 as the output. So that's -114 is the inflection point where we change from curving up to curving down. When x is 0, there's another inflection point, that is 20. We plug that in. Half of 0 is 20. So these are inflection points. Okay. So we could answer a bunch of questions here. We could say, where are the critical points? Critical points are at x equals -3/2, and there's a point there, -3/2, 9.875, and because the first derivative is changing from decreasing to increasing, negative to positive, that point is also a local minimum. There's no local maximum points, right? as far as where f is increasing, that would be these two intervals here. I'll use interval notation here. -3/2 to 0, and on the other side of 0 to infinity. F is decreasing over the other intervals from -infinity to -3/2. Right? And then from the other test, we learned that there is an inflection point at x equals -1, which does have a point, it's -114, and at x equals 0, so 0, 20 are called inflection points. F is concave up from -infinity to -1, and again from 0 to infinity, and f is concave down from -1 to 0. So we can answer a bunch of questions. There's no asymptotes here because there's no fraction to divide by 0. All right, so now we have enough to be able to sketch. So what we can do is use the f prime information to make a slope map, right? Where are we dividing this? We're dividing this at -3/2. Let's make an axis here. So maybe we can say, I'm not going to make this to scale here, except I am going to put some numbers in here. -2, -1, 0, 1, 2. But the numbers in the y direction are so much larger, I'm just going to label points. So I think what we would need is, let me change some things here. Okay, for the first derivative, we know that that breaks at -3/2, which is -1.5. And the function is decreasing here. It could have had a break at 0, but this was increasing and continued to increase. The second derivative, that broke at -1 and 0, and this was increasing, or concave up there, concave down there, concave up there. So we could sketch a function that goes through the known points. So we have a couple known points. Let's see, the largest y we have on here is 0, 20. So let's put that point in. 0, 20. We're going to define that point to be 0, 20 for scale, and that is an inflection point. Okay, we also have a point at -1, -14. So somewhere down here, I'm just going to label that point -1, -14. Oh no, it's +14, sorry. -1, +14. So maybe right about there. -1, +14. And then we also have, let's see, the point -3/2, 0. So right there. No, that's not a point. Sorry, that's our inflections. -3/2 is 9.8. So somewhere around here at -1.5, 9.8 that's a local minimum right there. These are inflection points. So now if I were to draw a curve in here, let's use okay. So here we have to go through this point, and this point. And in this region here, it is decreasing and concave up. So it must be looking like that. In this region from here to here, it is increasing and concave up. And at this point, it switches to concave down, but it's still increasing. And at this point, it switches to concave up, but it's still increasing. So here's a rough idea of the curve shape. Okay, that is pretty intense. There's a lot going on there, but being able to do that gives us a good indication of how we can use the first and second derivatives to connect to what's going on in the value of the function. All right, we're going to continue this with other applications of the first and second derivative test in part 2 video.